So, welcome everybody to iQuest seminars. Today it's my pleasure to have Elena Agostini from NVIDIA as a speaker. Elena actually was a colleague of mine at CNR in Italy, in Rome. We actually did a PhD at the same school together. But today she is an outstanding engineer in NVIDIA, and this focus is on network protocols, GPU direct technology, and I guess was in the past in the team, Davide Rossetti's team. And today she will talk about the new technology that NVIDIA provide to make the GPU at the center of the computing in the distributed systems. So Elena, feel free to start when you are ready, and enjoy the talk.
Thank you, Fabio, for the great introduction. Thank you also, everyone here for joining the seminar. In this presentation, I will give you an overview about what are DPUs and what is DOCA. I know there's a bit of confusion sometimes, so I would like to shed a light on all of these components. Starting from the hardware. So what are DPUs? So DPUs are smart NICs, NVIDIA smart NICs, that basically have a lot of components, hardware components on top of them, basically. So what happens is you buy your DPU, you plug it into your PCI slot of your host x86 system, and for free you have an ARM system. Because on the DPU you can find CPU ARM cores, by default, the basic version of the DPU, let's say, CPU ARM cores, a network card, and a number of hardware accelerators. And depending on the type of DPU that you have, like Bluefield 2 or Bluefield 3, you can find different types of different models of this hardware. So if you have a Bluefield 2, you're going to have a Connectix 60X as a network card, a PCI Gen 4 interface with the host, but also on the card. 8 ARM cores, and a number, as I said, of hardware accelerators for, to accelerate regular expressions, security or crypto tasks like IPsec, and so on. If instead you have a Bluefield 3, you have a Connectix 7 as a network card, a PCI Gen 5, 16 ARM cores, and still kind of the same list, but of course more powerful, of hardware accelerators. So, basically what happens, you plug in your DPU in your host system and you flash what we call the BFB image. That is the image that allows you to install firmware, drivers, operating systems, everything on the DPU. And in the, let's say, after that you do that, you can SSH into your DPU connected to your host x86 system, and you will end up having a remote Ubuntu server running on ARM. So it's basically another server, an ARM server. You can SSH into it. You're running in an Ubuntu environment, so you can build C, C++, Python applications, whatever. And you can take the advantage of hardware accelerators and network card. So this is the basic line of DPUs. Then when we talk about converged DPUs, it means that you, roughly speaking, have the same configuration, the same hardware, but you have also GPU on top of your DPU. And depending on the type of the DPU converged card that you have, you can have an A30 GPU or an A100 GPU for Bluefield 2 or Bluefield 3. So the good thing of a DPU converged card is that you have already the best PCI topology connecting all of these peripherals in the same board. So there is the best connection between the Connectix and the GPU. And so you can use the DPU in two modes. In the, let's say, CPU mode, that is the one I was explaining, where you can, again, SSH into your DPU, and you can run your application on the ARM cores of your DPU using the network card, the GPU, or the other accelerators. Or you can put the DPU in NIC mode. So when you put the DPU in NIC mode, basically you are shutting down the ARM cores. And the final effect is that if you're running an application on your x86 system, you can see the PCI peripherals of the DPU as regular PCI peripherals. So you can use the network card, the GPU, hardware accelerators from your application running on the host system. So depending on what you want to achieve, you can decide if you want to run your application on the DPU, on the ARM, or on the x86 system. So probably Intel cores, AMD cores, whatever you have. And this is just, I already said that, but I just want to put some focus on this. The good thing to have a DPU converged card is that you have the best PCI connection between the GPU and the network card. And this is crucial when you have GPU packet processing application where you want to receive packets directly in GPU memory at the fastest way possible without hitting system limitations or so on. It's nothing that you cannot do without the DPU converged card. As you can see here on the top of the picture, you basically can attach to the root complex of your host system a GPU and a network card, but you need to take care about the PCI topology, add an additional PCI switch, be sure that you properly configured everything and so on. Instead, if you plug in a DPU converged card in your system, either running your application from the ARM cores of the DPU or running it from the x86 cores of your host system, you can basically use GPU and network card at the fastest way possible, in the best topology possible, without worrying about anything. So this is one of the major advantages using DPU converged card when you are working with GPU applications. Okay, this was a kind of an introduction about DPUs, and basically I wanted to give you a sense on how you work with DPUs from a software point of view. Now let's dig into DOCA. So DOCA is the acronym for Data Center on a Chip Architecture, and basically it's an umbrella term to basically it encapsulates a lot of things. Tools, services that you can use for to deploy your application in a cluster of DPUs, for example, Dockers, containers, the BSB image I mentioned before that you can use to, flash it on your card and have an Ubuntu operating system on it, and so on. But there's also the SDK. So Docker SDK is just another SDK, like DPDK, like MPI. You have a C++ API that you can use to get, the best possible performance out of the NVIDIA hardware components. When I say NVIDIA hardware components, I mean the DPU, the hardware engines you can find on the DPU, the GPU, the network card. Thanks to DOCA, you can get the best out of those components in the easiest way possible, let's say. And what is important to understand is DOCA is not something that works only on the DPU. DOCA is a C++ SDK, and you can run it on the x86, you can run it on the DPU ARM cores, it's the same, right? It really depends on what you want to achieve. If you want maybe hardware isolation for your application, maybe you want to run everything on the DPU to not occupy any resource of your x86 system, or you don't care about it. You want to have your x86 system using the DPU just for the PCI peripherals and hardware accelerators. In both cases, DOCA API can be embedded, introduced in your C++ application. Just to give you a few examples about what you can do with DOCA, of course, there is a programming guide online. You can just go there, check all the libraries, applications, a lot of explanation, pictures, diagrams about what you can achieve, and a lot of different ideas that you can use to brainstorm about the task you want to accomplish. But for example, let's say you want to build a C++ application, Ethernet application and you want to receive Ethernet packets directly in GPU memory and process them as soon as they arrive in GPU memory. So maybe you want to use a combination of DOCA libraries like, of course, DOCA Core to initialize the environment. But then there is DOCA Ethernet, that is a library that allows you to create on a network interface, to send or receive Ethernet queues. Then you can use DOCA Flow to set hardware flow steering rules to each queue to say, okay, in this receive queue, I precisely want to receive only this kind of packets, like UDP packets or packets with just this source IP address. You can decide, you can play with all those rules. And then, as I said, it's a GPU application, so you want to directly receive packets in GPU memory, so you may want to use GPUNetIO to connect Ethernet queues to the GPU memory and control the network card from the GPU. I will spend, of course, more words. I will give you more explanation about DOCA GPUNetIO in the next slides. Other examples can be, okay, I want to run an application that is doing DPI with regular expressions. Well, there is DOCA DPI, DOCA regex that you can use to take the advantage of the RXP, that's the hardware accelerator for regular expression that you can find on the DPU. Or, for example, another very nice type of context. You have two applications, one running on the DPU ARM cores, and another one running on a host x86 cores. And you want to communicate, you want to establish a communication channel actually between the two applications because they need to exchange information, data, whatever. In this context, you can use DOCA communication channel to, again, establish a communication channel between the two applications and exchange data. Or maybe you want to just do some copy of some memory maybe residing on a x86 and you want to fetch it and move it to the DPU or vice versa, then you can use DOCA DMA to do that. So again, there's a variety of libraries you can use for different purposes, not all of them network oriented. They can only also be kind of resident applications between the DPU and the x86. Really depends on what you want to achieve. Now, I would like to focus on DOCA GPUNetIO. So DOCA GPUNetIO is just another DOCA library, as I said, mostly focused on GPU packet processing applications over Ethernet. To give you a bit of context, let's start from the beginning. So what is GPU Direct? GPU Direct is a family of technologies that allows you to put in communication the GPU with someone else in the system. Specifically, GPU Direct RDMA is about allowing the network card to directly access the memory of the GPU. So for example, you can program the network card to receive packets directly in GPU memory, bypassing system memory, avoiding additional CPU copies, staging copies, whatever. You can just directly receive packets in GPU memory. Or, of course, vice versa, you can instruct your network card to send data, fetching them directly from the GPU memory. So it's about GPU Direct RDMA, it's about moving data. And in order to achieve this, you need to, have the best topology to allow the maximum throughput in this network card communication with the GPU memory. So you may want to achieve what I was explaining earlier, a topology like this one, where you have an additional PCI switch between the GPU and the network card to have a dedicated PCI layer between the two. And again, have the best throughput in the data exchange between the two devices. But GPU Direct RDMA is only about moving data. So, and typically it's employed, as I said, in GPU packet processing applications. So when you have to receive data, for example, that in GPU memory, process the incoming data with some CUDA kernel, some CUDA task, some GPU workload, and then maybe you want to send the output again over the network, store the output somewhere in system memory. Really depends from application to application. But the point is, in this kind of applications, if you only have GPU Direct RDMA, it's super easy that the CPU becomes the bottleneck in this overall process because the CPU is acting as a man in the middle between the network card and the GPU. Specifically, what happens? You have, for example, the CPU that is invoking the receive primitive, which means that the CPU goes to the network card, let's say, asks to the network card to receive packets, and the network card receives packets thanks to GPU Direct RDMA directly in GPU memory. The receive primitive returns to your CPU process, okay, I received this bunch of packets, they are here in this memory location and so on. And then the CPU has to wake up some CUDA kernel, some GPU processing, GPU workload, to say, hey, you want to process packets, they are here, this is the number of packets, these are their features, characteristics, and so on. So as you can see, the CPU may not keep up with, network card, GPU, they're super fast, especially if you have a lot of receive queues to deal with, or you have high throughput line rate, all these kind of things. Additionally, you also have a lot of PCA transactions in this communication between, well, not between the CPU and the network card, but between the CPU and the GPU. So a lot of PCA transactions, a lot of waste of resources. And this is the motivation behind DOCA GPUNetIO. That is the DOCA library I mentioned. So DOCA GPUNetIO combines two GPU direct technologies. RDMA, as I explained, it's about moving data back and forth to GPU memory from the network card, but also GPU direct async. And specifically, GPU direct async kernel-initiated network communications. What it means? It means that you can move the control of the network card from the CPU to the GPU, and you can totally get rid of the CPU. So from an application like this one on the left side, you can get something like here on the right side, where basically you can launch a CUDA kernel that is totally independent from the CPU, and it's capable to receive packets and process them, or vice versa, produce data, produce packets, store them in GPU memory, and ask the network card to send those packets directly from the GPU memory. So again, it's about control, not about data transfer. And in this way, again, you can totally get rid of the CPU in the main loop of your application, in the critical path of your application. This is a generic overview about DOCA GPUNetIO. It has been released in DOCA 2.0 last April. And as I said, provides a control path solution for GPU real-time packet processing network application working over Ethernet. It has GPU direct RDMA, it has GPU direct async, as I explained, but it also has other features, like you can create GPUNetIO semaphores. They're objects shared between two CUDA kernels or between a CUDA kernel and a CPU core. And you can use those objects to establish a communication and synchronize their work. For example, you have a CUDA kernel responsible for receiving packets, and then you want to forward this information of how many packets have been received, where they are, and so on, to another CUDA kernel that is only responsible for packet processing. You can use a semaphore for that. I will show you a slide dedicated to it. Or if you want to, at a certain point in your GPU pipeline, provide information to the CPU core to say, okay, I'm at this point, I accumulated this data, these are the results, and so on. You can still use a semaphore shared between the GPU and the CPU. Another nice feature is that you can allocate with GPUNetIO a GPU memory location that is directly accessible from the CPU in a sense that, without using CUDA API. So you can use the GPUNetIO memory alloc function to say, this is going to be a GPU memory buffer, GPU memory area, but you need to map it so the CPU can directly access it without using CUDA memset, for example. You can just modify that memory from the CPU. And finally, a very nice feature that we used in mobile networks, I will give an example later, is the accurate send scheduling feature, where basically with GPUNetIO, you can prepare and send packets. And once you push the packet to the NIC, the network card will send them. But you can also program your send in the future. So you can associate a timestamp at a given subset of packets, a bunch of packets, and give this information to the network card, and the network card at hardware level will take care of sending those packets over the wire or the network at the right time in the future. So summarizing, we have with GPUNetIO less CPU cores utilization because the CPU is not involved in the critical path. You have a platform independent solution because it doesn't matter if you are on a DPU with ARM cores or an x86 with Intel cores, for example. If you have the same GPU, the same network card, and the same PCIe, of course, your application will behave in the same way. And the performance, we expect the performance to be quite the same in the two different platforms. As I said, there is less PCA transactions because, the CPU doesn't have to communicate nothing to the GPU. The GPU is totally independent. And finally, it also offers you a great high degree of scalability of your application. I will give you an example later, because you can serve multiple clients in parallel, because on the GPU, you can run multiple CUDA kernels in parallel. Now, I just want to put the focus on this item because we are looking for collaboration. So DOCA GPUNetIO is starting to be widely adopted by Ethernet GPU applications. but there's nothing preventing us to also enable the same technology over RDMA in DOCA. There is DOCA RDMA today, but it's a CPU-only library. If you're interested also in RDMA, or someone that wants to, has a use case to run over RDMA a GPU packet processing application, we are more than welcome to have a motivation to do GPUNetIO over RDMA and to establish a collaboration. So, I'm just spreading the knowledge just in case. So this is what I was describing. This is how we improved our NVIDIA Aerial 5G software with DOCA GPUNetIO, moving from a CPU-centric approach, where the CPU was mastering the communications, to a GPU-centric approach. On the left side, you have DPDK. Our previous implementation that was mostly based on DPDK, that was a CPU-centric software. And basically here, you can think about Aerial as a central software for multiple antennas, for multiple radio units. Each radio unit for us is a client. So there is, in 5G networks, there is a specific time slot where you have to receive packets from different clients. And so what happens? You create receive queues, one per client, and your CPU core receive packets from the first client. And if there are packets, notify a CUDA kernel responsible for the packet processing that a new bunch of packets is ready here and in this memory location and all the attributes, let's say. And then you move to the next, in the same CPU core, you move to the next client and so on until you reach the last client, and you circle back receiving in the first client, in the queue for the first radio unit. So what is the problem? The problem is that this is not a scalable approach, because the latency between two receive on the same queue increases if you increase the number of clients connected to your server. You can, of course, think to use multiple CPU physical cores. You cannot use CPU, let's say, software threads. You need CPU cores to keep up with the high line rate you need to sustain. But this, on the system, in a 5G, let's say, system, you don't have only Aerial running. You also have upper layer pieces of software running on the CPU doing other stuff. So it's super easy that you run out of CPU cores. And also the PCI bandwidth is heavily used because of all of these communications between the CPU and the GPU. So what we decided to do is we decided to move to a GPU-centric approach with DOCA GPUNetIO. So what we did is, right before starting the receive slot, we launch on the CUDA kernel, on the GPU, a CUDA kernel per client, per radio unit. And this means that as soon as every client sends some packet, it has a dedicated kernel running in parallel to the other. So definitely totally independent from other CUDA kernels. You have this dedicated CUDA kernel per client that is ready to receive and process packets as soon as they come into the memory. So in this way, we multiplied by 4 the capacity of the system, and well, actually even more. We'll see in the future. But this was the reason for which we were able to achieve such a high performance in Area 5G. Now, maybe this is redundant, but I want to add more details about how you can build with DOCA an application using GPUs, because a lot of people get easily confused. So when you have a GPU packet processing application, you have an initial phase on the CPU where you do the configuration, so the setup. And when I say setup, I say, as I mentioned before, use DOCA core to initialize the network card, DOCA Ethernet, DOCA flow to create send or receive queues, depending on what you want to achieve. And then you use DOCA GPUNetIO on the CPU, because GPUNetIO is actually composed by 2 libraries, a shared library having only CPU functions, and a static library having only CUDA device functions. So in the setup phase, you can use DOCA GPUNetIO CPU functions to allocate, initialize the GPU, allocate memory structures, create objects, whatever. And once you've done with the setup, you can launch the CUDA kernels on the GPU. From this point, the main loop of your application is happening on the GPU. The CPU can stay there, do other stuff, check sometimes the work of the GPU, but it's free to do whatever it wants. The main loop, again, happens on the GPU. So you may want to decide to run a kernel for, receiving packets and processing them, share the result, share packet information with other CUDA kernels, and so on. Or you can decide to launch CUDA kernels that in a loop produces some data and send this data over the network. Or you can do both, of course. You can launch whatever CUDA kernel you want on the GPU. This is a kind of a big picture of what you can achieve with DOCA GPUNetIO. So on the left side of the picture, this is the results of what you can achieve after the CPU setup phase, like a list of receive queues, each one Ethernet queues, each one having DOCA flow steering rules assigned. So for example, in receive queue 0, I want to receive only Ethernet packets coming from a given IP source address. In queue number 1, I want to receive only UDP packets. You play with these rules, you play with priorities. DOCA Flow is a super helpful, nice tool to do that. And you attach the queues to GPU memory. Once this is done, you can launch. This is just an example. You can do whatever you want, of course. But an example is that you can launch a CUDA kernel on the GPU, where each CUDA block is dedicated to a different receive queue. So for example, CUDA block 0 we receive from Q0, CUDA block 1 we receive from Q1, and you already know, thanks to DOCA Flow, which kind of packet you will get out of that queue. And then you can decide, okay, I want to dedicate this kernel only to the receive task. Maybe you want to do some kind of pre-processing, super simple pre-processing of your packet, but then you want to delegate a second CUDA kernel for the intensive data or packet processing. You can use a DOCA GPUNetIO semaphore. As you can see here, you can fill the next item of this semaphore. The semaphore, you can treat it as a ring buffer abstractors, basically. And you can fill the next item of the semaphore with a bunch of information you want to share with the second kernel and set the item to ready. The kernel responsible for packet processing is polling that semaphore and all the other semaphores, of course, in parallel, waiting to receive packets from the previous kernel. As soon as it sees there are packets, it processes the packets, and maybe it wants to continue some pipeline, providing its outputs to some other CUDA kernel or to some CPU core. And in that case, it can use another semaphore. Another example is that you can squeeze receive and packet processing in a single CUDA kernel. It really depends on how, the time spent by your CUDA threads in the block to do the packet processing, because maybe if you have a huge packet processing, you can increase the latency between two receive on the same queue. But it really depends. Of course, this approach is easier because in a single kernel, single block of this kernel, you have receive and process and at least packet pre-processing happening in the same place, avoiding additional synchronization with other kernels. Of course, here I'm saying CUDA block, but GPUNetIO gives you different flavors. You can receive, at block level, at warp level, and at thread level. So you can use maybe in a single block, multiple warps, each warp receiving on a different queue, for example. So you can play with all these flavors. And just to say, okay, we are not going in the mobile. DOCA GPUNetIO can be used in several different contexts, type of applications, security, network analysis, sensor networks, AI of whatever type. This is another example of how NVIDIA Morpheus use DOCA GPUNetIO. So Morpheus is our AI framework that you can use for security purposes to use basically AI on the GPU to accomplish security tasks of different types. What you're seeing here is a specific use case where Morpheus has to sniff the network and analyze a certain type of packets, for example, HTTP packets, and it has to detect online in real time if there is any security threat using an AI inference pipeline. So an example of architecture that we built is depicted in this picture. We have basically our system with a network card that is capable to sniff traffic from the network. And we have multiple receive queues connected to the GPU memory in the way I described before. Then Morpheus has, on a dedicated stream, a CUDA kernel that receives in a loop packets from those queues. Now, if you're not interested in HTTP packets, for example, it means that we want to receive TCP traffic. So in the initial configuration phase, let's say, we can set flow steering rules with DOCA flow saying, okay, in these queues, I only want to receive TCP packets. It means that the network card at hardware level will just discard non-TCP packets. So you have a first layer of filtering happening at the network card level, thanks to DOCA flow. But DOCA flow cannot work at, it can work on packets up to layer 4. So layer 7 application packet payload, it starts to be really tricky. So here in this case, for this reason, Morpheus decided to adopt DOCA GPUNetIO to receive TCP packets in GPU memory and then filter only good packets that, for example, in this scenario, good packets are HTTP packets. So basically Morpheus detects HTTP packets with only specific characteristics in the header and blah, blah, blah. And it stores relevant packet info in a GPU memory buffer. You can think that you pre-allocated a list of GPU memory buffer, each one is capable to hold a list of packet information. Once the first buffer is full of packet information, so we accumulate enough packet information, the CUDA kernel basically set to ready the first item of the DOCA GPUNetIO semaphores, which means the first buffer is full of packet info. You can unblock the AI pipeline to go in the buffer, read the packet information, and do whatever inference it has to do. And so this happens. There is a super tiny CUDA kernel waiting on the semaphore. It detects that the semaphore is ready, semaphore item is ready, and so it unblocks the AI pipeline on knowing that the packets are in buffer 0. So finally, I only, let's say, talked about the receive side, but I mean, trust me, there are also a lot of applications that want to produce data and send the data over the network from the GPU. And an example is still aerial 5G. In aerial 5G, there are, well, in 5G networks, you have time slots where you want to receive and process packets, but you also have a time slot where you want to produce data and send the packets over the network. In mobile network, though, you cannot just send the packets over the network, flash them over the networks, and that's it. You need to send them according to a specific pattern with respect to time. So you have 500 micro, and in 500 micro, you need to send a list of packets, but not all at the same time. The time slot is divided into 14 symbols, each symbol composed by 36 microseconds. So every 36 microseconds, you had to send a new subset of packets. And thanks to the accuracy and scheduling, that again is the feature that allows you to associate a timestamp to a set of packets. You can pre-prepare everything in software, push packets and timestamp to the network card. And again, the network card at hardware level, so without consuming any system or, let's say, software level, resources, the network card at hardware level will take care of sending the packets out over the wire, over the network at the right time. So mostly that's it. This was, as I said, an overview. There's a lot of references, links, blog posts. I can share these links with you so you can read more about it. And I want to reserve some, time in the meeting to have question answers. If you have any, let me know.
Okay, thanks, Elena, for the great talk. It's nice now we have enough time for addressing all the potential questions that our audience may have. So anyone wants to start asking things, of course, Elena, you don't have to disclose everything.
I have a couple of questions actually.
I was quite sure.
So thank you, Elena, first of all, for the talk. There are things that now I understand better about how this works, but I also have a few questions. So as far as I understand, if we have this converged DPU, basically we have on the DPU we will have both a CPU and a GPU. So now there are different combinations, of course. Like I could run something on the x86 CPU and offload something on the DPU CPU, or I could run something on the x86 CPU and offload something to the DPU, GPU, and so on and so forth. So how many, I mean, which of these combinations are actually possible? Like, can I run something on the host GPU, for example, and let it communicate with the kernel running on the DPU, GPU?
Yeah, so here, right, you said converged card, so you have a GPU here. So if you put the converged card in NIC modes, it means that you're shutting down the ARM cores. So what happens is all the PCIe peripherals on the DPU, like the network card, the GPU, hardware accelerators also, are then visible just as any other regular PCIe device to your host. So if you're running your application on your host system, you can build your DOCA CUDA application, of course, referring to the GPU here on the DPU, just through the PCIe address of this GPU. And you don't have to worry about anything, basically. And actually, this is what I suggest to start with, because it's just easier, right? You know your system, you know your x86 system, and you don't have to deal with ARM specific stuff, or for example, when you're running your application on the ARM cores in another scenario, you need to properly configure the OVS switch on the board to properly redirect network traffic in the right place. You don't have to worry about all of these details when you're working from your host x86 system. So typically what I like to do when I work with DPU converged card is I build my application, I'm running on x86, I put the DPU in NIC mode, so I use the network card and the GPU from the DPU, and then once it is done, if I need it, I can just, I don't want to say copy and paste because it's too naive, but I want to just port my application on the ARM cores of the DPU and run it over there. This is an option. Another option, depending on what you want to achieve, is like you can have two applications. So you have the DPU converged card in CPU mode, so blue field mode here. And so you have two distinct applications. The application running on the ARM that at that point owns the network card, the GPU, and the hardware accelerators. So you cannot see them from the host. And an application running on the host. And so what you can think about is you have this application running on the ARM, mastering all the PCIe devices on the DPU, waiting for instructions from another application running on the x86. And then you can use something like here, the DOCA COM channel or the DOCA DMA to give some message, signal, whatever information you want to pass from the x86 to the ARM. But it really depends on what you want to do. Of course, these add an extra latency in these communications.
Yeah. So like, could they use, let's say, this DOCA communication channel between an application running on the DPU, GPU, let's say on the host GPU?
On the DPU ARM cores here?
No, on the DPU, GPU. Okay, on the DPU ARM cores, yes.
Exactly. On the DPU ARM cores, you have an application here that, I mean, it's a CPU application, right? Using GPU NIC or whatever, and another one staying here. But again, these add an additional layer of complexity. So I'd really suggest you to start to implement something x86 and just using the GPU here. But
yeah, makes sense.
You can play with it.
I just have one last question, then I leave the floor to someone else. So if I understand correctly, all of this works with Ethernet, right? But what if I want, for example, to do GPU to GPU RTMA? So that should still be possible with other libraries, right? Like with, I don't know, GPU Direct or...
So, as I said, few considerations. So if you want to go GPU from GPU on different DPUs, yes, you need to do something like RDMA. So yes, in NVIDIA we have NVIDIA and other libraries that basically adopt these technologies over RDMA, but they are, let's say, you can read the purposes of those libraries are not, they are more super complex, super useful libraries that simulate a shared memory across in a cluster of nodes, for example, or InfiniBand or RDMA. So definitely it's an option. If you want something instead, if you want something simpler, because you have maybe one DPU, two DPUs with the GPUs and so on, as I said, at the moment, GPUNetIO works only on Ethernet just because we only have Ethernet customers. But if we want to establish a collaboration, and honestly, I have motivation to enable this over RDMA, we already have DOCA RDMA. We just need to enable the data path on the GPU. So I'm totally open to do that. I actually really want to do that in the next month. But if I have a good motivation, it would be just better for me to push for this RDMA enablement on the GPU.
Yeah, Flavio knows about some of the idea we had. We can discuss this later, maybe. Okay, thank you, Elena.
Thank you.
Thank you, Daniela. So Lorenzo is the next. Lorenzo, you are muted.
Sorry. Now you hear me?
Yes.
Okay. Thanks. Sorry. Yeah, thanks for the nice talk again. And then my question is very related to the last one of Daniele, and was if we can use the DOCA as an alternative to multi-GPU process that usually use MPI and CUDA framework. And if we can, which are the performance comparison between them?
Well, that's an interesting question to answer. Definitely you can. The difference is that anyway, MPI invokes functions from the CPU, or DOCA GPUNetIO invokes functions from the CUDA kernel. So it's more a matter of feature enablement. Like if you have something, if it simplifies your code, let's say having a CUDA kernel responsible to receive and process packets, for example, just in a single CUDA kernel, again, simplifies your code, simplify your algorithm. Well, that just makes sense without CPU intervention. Honestly, it's been a while since I worked with MPI, so I'm not fully updated on that. But again, they are different libraries. Definitely, they work on the same kind of ecosystem because we are talking about Ethernet connections. But as far as I remember, MPI has asynchronous callbacks that you can deliver to the GPU to take care of packets once they arrive, like once a certain event happens, unblock something on the GPU. So it's a kind of an asynchronous process, kind of batching all of this stuff on the GPU. Here is some more real-time stuff. So you have a kernel. I don't want to say persistent because persistent means for the overall execution of the application, but persistent for a while, that stays there on a while until it can be forever, it can be for a limited time. It depends on your application. Stays there, it's super reactive and calls in a loop your network card. As soon as packets are arriving, it is immediately able to process those packets. Performance really depends on the application. I can say that if you download the DOCA framework, there is the DOCA GPU packet processing application using all of the technique I explained in this talk. And for example, I was able to receive and do a super simple analysis of the header of UDP packets at 100 gig with one receive queue. So of course, then at that point depends on how long it takes for you to process incoming packets to get the overall latency of your system. But from a performance point of view, I think definitely GPUNetIO will not be a bottleneck.
Okay. And then I have a last short question. is that we call all the hardware as DPU, but I'm wondering if it's related in the DPU in the sense of processing memory. So if in the card there's some memory bench that are processing memory enabled, or it's only a name similarity.
No, sorry, sorry, maybe I didn't get your question.
I think I can pull out this. Lorenzo asked if there is some smaller accelerator within the SmartNIC, which for example, some SRAM that also accelerate the computation. In this case, the SRAM is not just the SRAM, but it's also have some compute capability. It's super fancy, Lorenzo. I think we are pre-silicon level in many different things. I don't know.
I'm not aware of. I see. I'm not aware of that, honestly. I mean, I don't. It's not. It doesn't mean that it's not there, but I didn't heard anything about that on the SmartNIC. There are hardware accelerators for regular expressions, for crypto compression, so you can do IPsec at hardware level, regular expression at hardware level, but they are kind of separate hardware engine on the DPU.
Okay, thanks.
Any other question from the audience?
I have a question, if possible.
Yeah, Leah, go ahead.
Okay, so first, thank you for the nice talk. My question is more oriented to the DPU, its structure, and the purpose that has driven its development. I mean, the main purpose that has driven the development of a DPU is more oriented on having a fully optimized node for do computation, or it has been started meant to communicate with the host system. I mean, is the development driven in order to have some computation that has been tested on an x86 system and then ported to the ARM cores and run it in the best topology, or the communication between the host system and the DPU has been a key point from the starting point of the development? I don't know if I've been clear. I'm sorry.
Yeah, I mean, I'll try to answer. Let me know if I address your question. So, no, it's not the communication with the host. Honestly, the communication with the host is something that we thought at the very early, stage of DOCA, but was not the focus. It was just another feature enablement because it can be useful. But the whole point is that when you plug in a SmartNIC on your system, you take the advantage of system on a chip, and you can take the advantage of hardware isolation. So your host system doesn't have to take care of computing stuff, processing of several things, especially, of course, network oriented. Having that on a DPU, we have a super powerful network card. Is more like you have your application, and ideally you can have a cluster of DPUs connected to some x86 systems, but the DPU are totally independent to your x86 system. So the idea is to, again, have as the acronym saying, a data center on this chip that is totally independent, and additionally can also communicate with the x86. That was and is the intention.
Okay, thank you.
Probably we may have another one, probably the last one. Someone else from the audience, or I just asked? Okay, I have one, at least I have more, but I don't want to use your time, Adam, today. In case of collaborations or these kind of things, there is some system at small scale that is available for testing it, or just to play with DOCA and also Bluefield 3. Some academic program that maybe we can consider for a potential collaboration. So we have to find a different setup where we try to actually offload part of the work to you directly.
So the last thing is the fastest one. If we let's say if you float some of I mean, if you have an application, right, and you want to have a super fast way to test it, you just give it to me, we can work together, and I can run it on our internet server. So that's obviously the fastest way possible. I am not aware of any academic program, especially for Bluefield 3, but let me come back to you with this. I don't want to say 100% no. Let me come back to you on this.
Yeah, because I suppose that I mean, we have a bit of manpower to support in case potential collaborations. Otherwise, if you have to do most of the things, it does not make sense for us just sending out applications.
Sure. No, I understand. Well, let me come back to you on this.
Okay, that's great. So if we don't have any other question, let me thank again Elena Agostini from NVIDIA for our great talk, and I look forward to see you in the next seminar. I don't remember when it's scheduled, but we'll send out an email with a reminder and with the speaker. So Elena, and probably we should schedule another call, probably the internal one, to discuss, because our idea is to work in that directions for SE supercomputing 24. So I think there is a common goals that we want to achieve. Maybe we can do this together.
Absolutely, sure.
Okay, so guys, thank you again for joining the ICRES seminars, and see you soon.
Thank you, guys. Bye-bye.
Thank you. Bye.
Thank you.
Thank you. Bye.
Bye-bye.